Evenly distributing endpoints on a sphere. I need an algorithm that can give me positions around a sphere for endpoints, less than 20, probably, that vaguely spreads them out. There's no need for perfection, but I just need it so none of them are bunched together. This question provided good code, but I couldn't find a way to make this uniform, as this seemed 100% randomized. This blog post recommended had two ways allowing input of number of points on the sphere, but the Saf and Kuijlaar's algorithm is exactly in pseudocode I could transcribe, and the code example I found contained node k, which I couldn't see explained and ruined that possibility. The second blog example was the golden section spiral, which gave me strange, bunched up results with no clear way to define a constant radius. This algorithm from this question seems like it could possibly work, but I can't piece together what's on that page into pseudocode or anything. A few other question threads I came across spoke of randomized uniform distribution, which adds a level of complexity I'm not concerned about. I apologize that this is such a silly question, but I wanted to show that I've truly looked hard and still come up short. So, what I'm looking for is simple pseudocode to evenly distribute endpoints around a unit sphere, that either returns in spherical or Cartesian coordinates. Even better if it can even distribute with a bit of randomization, think planets around a star, decently spread out, but with room for leeway.
In this example code, node k is just the kth node. You are generating an array endpoints and node k is the kth from 0 to n1. If that is all that is confusing you, hopefully you can use that now. In other words, k is an array of size n that is defined before the code fragment starts, and which contains a list of the points. Alternatively, building on the other answer here, than using Python. If you plot that, you'll see that the vertical spacing is larger near the poles, so that each point is situated in about the same total area of space. Near the poles there's less space horizontally, so it gives more vertically. This isn't the same as all points having about the same distance to their neighbors, which is what I think your links are talking about, but it may be sufficient for what you want and improves on simply making a uniform lat/long grid.
This is known as pecking points on a sphere, and there is no known, general, perfect solution. However, there are plenty of imperfect solutions. The three most popular seem to be: create a simulation. Treat each point as an electron constrained to a sphere, then run a simulation for a certain number of steps. The electron's repulsion will naturally tend the system to a more stable state, where the points are about as far away from each other as they can get. Hypercube rejection. This fancy-sounding method is actually really simple. You uniformly choose points, much more than n of them, inside of the cube surrounding the sphere, then reject the points outside of the sphere. Treat the remaining points as vectors, and normalize them. These are your samples, choose n of them, using some method, randomly, greedy, etc. Spiral approximations. You trace a spiral around a sphere, and evenly distribute the points around the spiral. Because of the mathematics involved, these are more complicated to understand than the simulation, but much faster, and probably involving less code. The most popular seems to be by Saf et al. A lot more information about this problem can be found here. The Fibonacci sphere algorithm is great for this. It is fast and gives results that at a glance will easily fool the human eye. You can see an example done with processing, which will show the result over time as points are added. Here's another great interactive example made by Ekman. And here's a simple implementation in Python. 1000 samples gives you this.
What you are looking for is called a spherical covering. The spherical covering problem is very hard, and solutions are unknown except for small numbers of points. One thing that is known for sure is that given n points on a sphere, there always exist 2 points of distance d equals 4 CSE caret 2 backslash pi n 6 n 2 caret 1/2 or closer. If you want a probabilistic method for generating points uniformly distributed on a sphere, it's easy. Generate points in space uniformly by Gaussian distribution. It's built into Java. Not hard to find the code for other languages. So in 3-dimensional space, you need something like. Then project the point onto the sphere by normalizing its distance from the origin. The Gaussian distribution in n dimensions is spherically symmetric, so the projection onto the sphere is uniform. Of course, there's no guarantee that the distance between any 2 points in a collection of uniformly generated points will be bounded below, so you can use rejection to enforce any such conditions that you might have. Probably it's best to generate the whole collection and then reject the whole collection if necessary. Or use early rejection to reject the whole collection you've generated so far. Just don't keep some points and drop others. You can use the formula for d given above, minus some slack, to determine the minute distance between points below which you will reject a set of points. You'll have to calculate n, choose 2 distances, and the probability of rejection will depend on the slack. It's hard to say how, so run a simulation to get a feel for the relevant statistics.
If you want some more now, please consider liking and subscribing.